Hi, Professor. This is my submission to our assignment 7. Here we have 4 questions. First, the question is a hash table that hashes all value to the same slot is essentially equivalent to what other data structure? So a hash table that hashes all values to the same slot is essentially equivalent to the linked list data structure. Multiple values are hashed into a same slot, and this is called separate chaining or open hashing. Each of the value in the slot are linked to each other in order of their insertion. Second question is analyze the hash function that we discussed in the lecture slides. Elaborate the benefits and drawbacks of each function. So first is lose-lose function. One of the benefits of function is simplicity. It is also easy to understand. That could be a good starting point to learn hash functions. You just add ASCII code or Unicode character value of all the alphabet in a word and return that. This could cause many collision, and we lose the benefit of all one time in a hash table. Therefore, we can say the drawback um, is that, and the hash value is not always unique, and the algorithm is also slow as it causes a large number of collision. Second is the RS hashing hash. Similar to loss-loss, RS hash is also designed to be a very simple hash function. It will still cause collisions, but it's a better hashing algorithm than loss-loss since it minimizes the collision by multiplying two big odd numbers to produce hash value. Also, it will run at approximately same time as loss-loss, which is not fast. It has a great distribution of hash values, and it generates a long hash by multiplying two big odd numbers and adding ASCII code value to it. The third is the DJB2 hash. So it is similar to the RS hash, but improves on it by adding another step of bitwise and to generate the 32-bit long hash to reduce collision. It is one of the quickest string hashing algorithm, and also has a great distribution of hash values, and as it uses multiplication of large prime number with the odd number along with bitwise and to produce a 32-bit hash. It is good for bucketing in the hash table. Very few lowest bits are used, but as a 32-bit hash algorithm, it is not good. As for generating 32-bit result, it only does bitwise. And with the same 32-bit number, let's say B capital A and AB will have the same hash value. So even for a two-character long string, the hash value is not unique and the collision can happen. It has a very limited best functioning use case where hash table needs to be specific size with specific key characteristics. Fourth is the SBDM hash. Although SDBM is not very good for cryptography, it works well while generating the hash for alphanumeric characters, strings, or sequences. It also works well uh, where there is a high degree of variance in a given set. It is better than a DJB2 hash in case of collision, and it improves the hash function by adding multiplication of hash values, employing shifting of digits, and addition of multiplied values, and the subtraction of previous hash. Hence, it generates unique values, reducing the number of collisions. Also, SDBM is fast compared to DJB2 hash along with cryptography. SDBM is not good in case of networking or hashing for DNS datasets, as two different DNS can change by 1 bit, and that causes minimum abelian effect of SDBM. Changing 1 bit from DNS domain changes hash by 1 bit. So the third question is analyze the two methods of resolving collision in hash table that we discussed in the lecture slides. Elaborate the benefits and drawbacks of each method. So first is open addressing. So if a collision occurs, address is occupied, then the index increases until the next open slot is available for storage. There are several research for the next slot. And also we have the linear probing. Current occupied index value is increased by a fixed amount to check for the next open slot. Linear probing is very easy to compute, but it also suffers from the clustering problem where consecutive numbers can start to form a group starting to occupy adjacent slot, and it becomes like time consuming to look for the next free slot and search for an element. Then it's quadratic probing. The current occupied index value is increased based on the quadratic equation to look for the next free slots. Quadratic probing reduce the clustering problems. The difficulty level of the problem is based on the difficulty level of the quadratic equation. The third question is, what strategies and issues should you consider when you are resizing a hash table? What are likely complications and how would you address them? So there are two scenarios when you need to resize hash table, and both of these situations are depending on the load factor. So first, if the load factor gets too large, resulting in like slower insert, deleting, or searching operations close to big O(n), then we need to increase the size of the table to maintain average complexity. If the second is if the load factor drops down too low, resulting in waste of memory, then we need to reduce the size of the hash table. And in both scenarios, we need to maintain the load balance, the complexity of the performing this task, as well as the new hash function to map the new size, the addition of elements from the new table to the old table to the new table, the amount by which the new hash table should be resized, and the creation of the new hash table itself must be taken into account when creating a new table. Also, if open addressing or chaining are used in the previous hash table, we must choose whether we wanted to alter strategy in following table to avoid frequent resizing and complexity associated with the open addressing and chaining, which is covered in the previous. Typically, the most recent operation that causes the load factor to tip is taken into account when resizing the hash table. For instance, if the most recent insertion operation causes a load factor to exceed a certain threshold, then we need to increase the size after performing that insert operation. And it's a standard procedure to reduce the size by half of the hash table's initial size when decreasing and to double it when expanding. In order to avoid clustering and collisions in the new table, one of the most effective ways to grow the size of the table is to double it and then round up to the nearest prime number bigger than the doubled amount. Similarly, while reducing the size of the table, one more parameter we should consider is the new hash function, which will transfer elements from the old table to the new table. All of the transferring should be completed in O(n), where the n is the number of the elements. The new hash function should evenly distribute the previous element as well as the new element to avoid further clustering and resizing complications in the newly generated hash table. An efficient way to perform hashing is to use a universal hash, where a hash function is randomly selected from a group of hash functions. Thank you, Professor.